Let's continue our drivetrain development. Create a new script named Gearbox. This will be one of two parts that make up the vehicle's gear train. The job of the gear train is to manipulate the power coming out of the engine to better suit the vehicle's current operation. We primarily do this through torque multiplication, where a difference in gearing is employed in order to vary the torque and speed of the output in relations to the input. The exact sizing difference between the gears is called the gear ratio and is used to describe what happens to the torque and speed at the output in relations to the input. Please note that power, assuming no losses, remains the same between the input and output, as power is a product of torque and speed, and thus the laws of thermodynamics remain obeyed. Gear ratios are helpful in drivetrains as they allow us to trade the speed of our output for higher torque, and vice versa. When we're at a standstill, we want to get up to speed quickly, which requires a lot of torque, and thus a high gear ratio is needed. This means, however, that our wheels won't spin that fast before our engine runs out of revs and hits redline. We can try a lower gear ratio to increase our top speed, but this will in turn result in a decreased rate of acceleration. You should now be able to see where the gearbox comes into play, allowing us to swap gear ratios on the fly in order to meet the acceleration and top speed demands of the driver. We can continue adding gear ratios to our gearbox to make power delivery throughout the speed range as efficient as possible by ensuring our engine remains in the power band. With gear ratios, we're also able to run our output in reverse, allowing our vehicle to back up. For our real-time gearbox implementation, what we need is a way for us to connect our engine up to the wheels and multiply its output by some predefined gear ratio that we can update on the fly by changing gears. Let's use that knowledge and implement a gearbox. In the gearbox script, we'll first create an array of floats to store our gear ratios, a float to store the shifting time, an int to store the current index of the gear we're in, and a few bools to store the current shifting state. Then in the update method, we'll register player inputs that we'll then use in fixed update, where we'll start either one of two coroutines when we shift up or down respectively. These trigger IEnumerators that store our shifting logic that shifts to neutral, picks the next gear, wait the pre-allotted shifting time, and then shifts into that next gear. After our shifting logic, our gear train will multiply the downstream torque coming from the engine and the upstream angular velocity coming from the wheels by the current gear ratio before sending them either up or downstream respectively. We'll enable this functionality once the rest of the drivetrain is in place, but for now, we can play around with our gear shifting logic. Don't forget to set the gearbox to neutral on startup before saving the script, attaching it to the drivetrain empty, and adding gear ratios and setting a shifting time. Hit play and try shifting up and down while paying attention to our current gear ratio. Looks like it's shifting properly. One last thing I'll add is a quick and dirty gear indicator to illustrate the current gear we're in. And with that, we're able to easily shift from reverse to neutral to top gear and all the way back down again. The gearbox is just one of two essential parts of the gear train, with the second being the differential, or diff for short. Just like the gearbox, the job of the diff is to do further torque multiplication through a gear ratio we call the final drive. The diff also has the job of splitting the power of its input between its two outputs through a set of spider gears, which is where the secondary function of power manipulation, torque vectoring, comes into play. For today, we'll be implementing an open differential, which splits torque exactly 50-50 between both wheels, but sends more power to the wheel with less resistance. I'll be leaving resources in the video description that explain the mechanics of differentials as well as a better understanding of torque vectoring. But for our real-time implementation, the gist of it is, our diff will act as a final torque multiplier and splitter between the wheels and the rest of the drivetrain. Back in Unity, create another script named Differential and open it up. Just like the gearbox script, this will have a gear ratio we'll set called the final drive, as well as two functions for getting the downstream torque to the wheels and the upstream angular velocity to the engine. As this will be an open differential for now, the torque for each wheel will simply be the product of half the incoming torque multiplied by the final drive, while the upstream angular velocity will be the average of both wheels' velocities multiplied by the final drive. Again, these two functions will be commented until the rest of the drivetrain is in place. So for now, save the script and attach it to the drivetrain, and simply define a suitable final drive ratio and hit play, just to make sure everything is still functioning properly. And with that, we have one more drivetrain component to add before connecting everything together and going for a drive.